You slice your finger on a kitchen knife. A bead of blood rises, bright red, and you do what everyone does. You reach for a bandage. But you are already too late. In the 15 seconds it takes you to find the box, roughly 250,000 platelets have thrown themselves into that cut, and the bleeding has started to stop. On its own, with no instruction from you. You didn't decide that. You couldn't have. The paper cut last week, the shaving nick, the scraped knee when you were 7. Hundreds of times across your life, your blood has run one of the most precise operations in all of biology, in seconds, and you have never once felt it happen. Here is the part that should stop you cold. Your blood spends every second of your life trying to stay liquid. It has to. A clot in the wrong place can kill you in minutes, and yet the instant you are cut, the same blood turns solid in one exact spot, seals the hole, and nowhere else. Doctors have a word for this: hemostasis. It is Greek. It means the standing still of blood. So how does your blood know where to turn to stone? And harder than that, how does it know where to stop? The answer changes everything you think you know about a wound, a scab, and the invisible tightrope between bleeding and clotting that you have walked every moment you have been alive. One thing before we go under the skin. I'm a board-certified hematologist. Blood is what I've spent my career studying, so everything past this point is the real mechanism told straight. Let's start with the vessel itself, because nothing else can happen until it acts first. The moment the wall of a blood vessel is torn, it does the simplest thing possible. It clamps down. The muscle in its wall squeezes, narrowing the channel, throttling the flow like a kink in a garden hose. That alone buys a few seconds. But a squeeze is not a seal. Something has to fill the hole. That job falls to the smallest things in your blood: platelets. Here's what's strange about them. They're not even whole cells. They are fragments shed from giant parent cells in your bone marrow, and your marrow makes roughly 100 billion new ones every single day. A drop of your blood holds millions of platelets. They drift through you, flat and smooth and silent, living about a week, doing nothing at all, waiting for one signal. In 1882, an Italian pathologist watched living blood under a microscope at the exact moment a vessel was injured. He named these fragments piestrine, little plates, and he saw them do something nobody had described. When a vessel tears, its smooth inner lining breaks, and the rough material underneath is suddenly exposed. The platelets feel it. Within seconds, they transform. They swell, they sprout spiky arms, they turn violently sticky, and they hurl themselves into the gap and into each other, piling up, plugging the leak with their own bodies. This is the first plug, and for a small cut, it can be almost enough. But here's the problem: it is soft. It is a sandbag wall thrown up against a flood, and it will not hold under pressure. It is not a repair. It is a stalling mechanism, buying time for something far larger to arrive. And what arrives is a chain reaction. Dissolved in your blood right now, completely invisible, is a cast of proteins. Roughly a dozen of them, numbered like characters in a script. They are the clotting factors, and each one sits switched off, waiting, arranged in a strict sequence. When the wound flips the first one on, that one activates the second activates the third, straight down the line. Of course, this is an oversimplification, but here's the trick. Each step does not just pass the message along, it amplifies it. One activated factor switches on thousands of the next. A whisper becomes a shout, becomes a roar in a fraction of a second. Scientists call it a cascade, a waterfall, and the picture is exact. In 1964, two separate teams landed on the same idea in the same year. A falling chain of proteins, each one tripping the next. The whole cascade drives forward a single finish. At the very end, a protein called thrombin grabs a soft, dissolved material in your blood, called fibrinogen, and snaps it into threads. The threads are called fibrin, from the Latin word for fiber, because that is exactly what they are. They weave through the soft platelet plug, lace around it, form a mesh, and catch red blood cells as they rush past. The loose sandbag wall is suddenly stitched into something tough and stable and lasting. It is a true clot. And how do we know every link in that chain truly matters? Because of what happens when just one of them is missing. There is a condition present from birth in which a single clotting factor is absent. 1 out of the dozen. It strikes about 1 in 5,600 boys. Without that factor, the cascade stalls partway down. The wall can never be finished. A minor injury bleeds and bleeds and will not stop. This condition is called hemophilia, and it moves silently through the royal houses of Europe. Queen Victoria carried it and passed it on to the thrones of Spain, Germany, and Russia. One missing protein, and the whole magnificent chain comes apart. But the deepest part of this is not that your blood can build a wall. It's where the wall stops. Go back to what your blood just did. It turned itself solid, on command, in that one place it was needed, which should raise the question you have not been asking. Why did it stop just there? Why didn't the clot keep growing, creeping up the vein, turning more and more of your blood into stone until it reached your heart? Because that exact power, pointed the wrong way, is lethal. A clot that tears loose can lodge in your brain as a stroke, or deep in your lung and choke off your breath. And that same runaway clotting inside a coronary artery in your heart is what causes most heart attacks. Heart attacks and strokes are the 2 leading causes of death on Earth. The system that saves you from bleeding out is, turned against you, the most common way a human being dies. So your body does something almost unbelievable. At the very instant it is building the clot, it is also holding it back. The healthy vessel lining all around the wound is actively anti-clotting, telling the growing wall, not here, not one cell past this line. Other proteins surround the clot and cap it, fixing it to the exact size of the hole, and no larger. These breaks have names. Antithrombin drifts through you constantly, hunting down loose thrombin and switching it off the instant it strays past the wound. Protein C and protein S chew through the activated factors mid-cascade, so the chain reaction burns out instead of running forever. And here is the most elegant part. When thrombin reaches the healthy vessel wall, a protein on that lining called thrombomodulin grabs it and flips it, turning the very molecule that was driving the clot into the signal that stops it. The clot's own engine used against it, right at the edge of the wound. Take those breaks away, and the math turns monstrous. One small cut could turn the vessel solid, then the vein, then keep marching towards your heart until you were one clot all the way through. And later, once the vessel beneath has quietly healed, a cleanup crew moves in and dissolves the clot away thread by thread until your blood runs clear and liquid again, as though nothing had ever torn. This is the real answer to why a cut stops bleeding. Not simply that your blood can clot, that your blood can clot in one place, at one time, to one exact size, and then take it all back down. Every second you are alive, your blood is solving a problem that should be impossible. Stay liquid everywhere. Turn solid on demand in a single spot. Then clean up after itself and vanish. Lean too far one way and you bleed. Too far the other and you clot. And your body holds that line for you silently billions of times for your entire life without ever once asking your permission. We look at a scab and we see something ugly. Damage. A flaw to pick out, to cover, to be rid of. But what if a scab was never damaged? What if it is the visible edge of the most sophisticated emergency system you will ever own? A wall that was designed, built, and finished before the pain ever reached you? What if the thing you keep trying to peel away is proof that your body already saved your life? So the next time you cut yourself and a single bead of blood rises to the surface, stop and look at it for a second. Because in that moment, hundreds of thousands of platelets are already flinging themselves into the gap. A dozen proteins are firing in sequence, turning liquid into thread, and an unseen hand is drawing the line, telling the wall precisely where to stop. The plug, the mesh, the balance. All of it built in minutes, all of it exact. All of it finished before you ever reached the box of bandages. You will still reach for the bandage. Go ahead. Peel it, stick it on. But the real bandage was never in the box. Your body wove it first, out of nothing but your own blood. And most of us never even knew. I've spent my career studying blood, and this part still gets me. Everything you just watched, your body will do again the next time you bleed without a word to you. Now at least you know what it's doing. Thanks for watching. If you found this interesting, like and subscribe for more. Got a suggestion? Drop it in the comments. I'll see you in the next one.